Okay, good morning, everybody. Welcome to the first lecture of Control Systems 1. My name is Emilio Frazzoli. I will be the instructor for the class. And, okay, so what is this class about? This class is about control systems. Have you ever seen one? Probably not. You've been using them, even though you may not realize that all the time. Actually, control systems is something that has been called the hidden technology. It's something that is probably in every single piece of technology that you're using, or every single piece of equipment that you're using. In this picture, what we see is actually just a list of all the control systems that are actually running in your car as you drive, and you may not realize that. Okay, this is something that is really everywhere. Something is keeping the temperature of this room roughly constant. Doesn't matter what is the weather outside. Doesn't matter how many people are in the room. And you have many other examples. So the technology is widely used, very successful. It's hidden. You don't see it. You don't talk about it. Except in some instances where essentially where disaster strikes, right? So when your control system all of a sudden doesn't work anymore, and then you tend to notice that, okay? So let me show you some, actually I had to exit this and show you some examples. Okay, where is it? Okay. This is some videos on control systems that I just collected from random places on YouTube. This, for example, is a nice demo that some colleagues at Georgia Tech did recently, and of course it's not working. Yeah, whatever. Okay. This one is working. Okay. Actually, this is my baby. This is some video from one of the cars that we're actually driving in Singapore. Okay, it's a company that I started a few years ago. Okay, and then you see, even though we do have a driver inside the car, the driver is not touching the wheel. Okay, and then in this case, what you can imagine is that we have a number of cameras, other sensors, called LiDAR. These are like laser rangefinders. Essentially, give us a 3D view of the world around us. Radar, GPS, inertial sensors. All of this data gets fed into a computer, and this computer sends commands. These are the control signals that turn the wheel. Push the gas pedal, push the brake pedal, turn the blinker on, left, right, all these kind of things in such a way that the car drives by itself, hopefully without hitting anybody or anything, okay? So these are all like, number of, good things that are happening in this case, okay? But, sometimes you also find some other interesting videos. Okay, so this is actually a video of, this was during the early years of the F-22 program. This is one of the like most modern fighter jets.
In 1992,
developed
piloting an Air Force
in the U.S. Right. So what you see here is that the pilot is trying to land, and then something weird is happening with those elements, right? And yeah, it was no good. Okay, so this was a case in which the control system was not properly designed. In that particular case, what happened is that the control system coupled with the pilot and the way that the pilot was actually controlling the aircraft resulted in this form of instability, and then you see what happens, okay? So that's why what I say is this is the hidden technology. It's everywhere. As long as it works, you don't even realize that, this control system is there. But when it doesn't work, you very quickly find out, okay? So let's make sure that you kind of like want to make sure that you don't get famous by having one of those, like a big, like a disaster things, okay? Boring is better, okay? So when we drive people in our cars, our objective is that we want people to be as bored as possible. In the sense, nothing exciting happens in the car, and they feel safe, and, they can fall asleep or, do whatever else they like, okay? So let's get, okay, so what is the course about? The course is about dynamic control systems. In other words, these are systems that evolve over time. This is what we mean by dynamic, in a sense, okay? What do we mean by systems? We will talk more about that in a few minutes, but essentially these are objects that actually have some inputs and some outputs, okay? So this will be our definition of system. Every single engineering class that you've taken probably has their own definition of systems, okay? For us, as we will see, this is something that takes some signals as an input, right? So take some input, for example, the angle in the steering wheel or the angle in the gas pedal, and then generate some output that is the position of the car, the speed of the car, and so on and so forth. Okay? The class will be split into three main parts, okay? So these are the three main steps, the three main building blocks in developing your understanding of control systems. The very first step is modeling, okay? So essentially, we need to start figuring out how, given a certain object that we want to control, how do we identify what are the inputs, what are the outputs, how do you write some mathematical relationships between those inputs and those outputs that allows you to understand what will happen if you give some input and what kind of output you will have, okay? Because then, really what you would like to do is you have a pretty good idea of how you want your output to behave, okay? So now what you have to do is figure out what are the right inputs that you have to provide to the system in such a way that you get the output that you want. For the car, I have a pretty good idea that I want my car to drive along the road, right? Don't get on the sidewalk, don't hit people, and things like that. So now what we have to figure out is what is the steering angle that I need to provide as an input in such a way that my car will drive on the road, okay? I don't want to hit people, so I have to figure out what is the, but also I want to make progress, right? So I need to figure out what is the angle on the gas pedal in such a way that I will have a speed that I want, but also maybe what is the angle on the brake pedal in such a way that I brake for people, I brake for other cars, so that I don't hit anybody, okay? First part is modeling. So how do we make all of this more precise, mathematical, so that we can actually operate on that in some systematic, good, principled engineering way, okay? Given that modeling effort, so essentially reduce all these systems to some mathematical equations and formulas, what we want to do is to develop tools that allow us to understand whether or not the behavior generated by the system is actually something that we like or something that we don't like, okay? And so we will look at certain properties, for example, stability, other things like, stability is really about, will my airplane crash into something, okay? Or will my airplane fly safely, okay? And then you can think of other things like performance, for example, is the ride in the airplane comfortable, or is the airplane kind of like jumping up and down and, making very sudden motions and things like that, okay? So these are all properties that we will look at, and this is the second part that we will call analysis. And then the last part is really, okay, so I know how to represent my system in mathematical equations and formulas. I know how to determine whether or not my system is performing well. Is it stable? Is it safe? Is it comfortable? And then the third part is, okay, so now how do I design my control system in such a way that my system behaves the way that I want it to behave, okay? These are the three parts of the course. Questions? So far, so good, okay? Okay. From the point of view of the tools and the approaches that we will use, we will concentrate on systems that can be modeled by what are called ordinary differential equations. So essentially, these are differential equations which have as independent variable time, typically time, okay? And then these are equations that will involve the value of the signals over time, maybe their derivatives, first derivative, second derivative, and so on and so forth, okay? What we will do in this course is learn about a number of techniques that go under the name of classical control, okay? These are techniques, these are essentially the very first techniques that were developed by controls engineers, when they started developing these kind of control systems. And, we are talking about probably the 60s, okay? So this is when, actually it's a little bit earlier. I would say around the, like a Second World War, okay? So we're talking about like the 40s, 50s, 60s, where people started really thinking about how you design control systems that, for example, this was during the war, okay? That kind of thing, that, usually gives some, motivation to develop new technologies, okay? And, a lot of this work were about, for example, how do we maintain the gun in a ship, right? How do you keep the gun pointed in the right direction even though the ship is moving, right? Because of the waves and, it's a ship on the ocean, okay? How do you keep following a radar track, right, as an airplane is, for example, is moving, and things like that. Okay. Now, at the time, people didn't really have that many computers, right? Actually, at the time, computers were people who were doing calculations by hand. Okay. So what you will see is that a lot of these techniques are actually very powerful techniques that, at the end of the day, involve some graphical methods, okay? So these are all techniques that you can use to do some control design, literally, with a piece of paper and a pencil, okay? Maybe a ruler, okay? Are these the most advanced techniques that are used today? Not really. There are, many other techniques that you use today with, making more reliance on computers and, things like that. On the other hand, I think it's very important to develop a very good understanding of these techniques, because these are the things that allow you to get an idea of what your computer program should output, okay? So these are the things that allow you to get an idea, just by hand, by intuition and sketching on a piece of paper, of what your control system should look like, okay? So that you just don't trust the black box. Because sometimes you make a mistake, and the black box, maybe you make a mistake in the input, what you type in your program, and then what you get as the answer is something that is the correct answer given your bug in the program, and so it doesn't make any sense. So do you want to trust the black box, or you want to have an idea of what the solution should look like, okay? So I think it is very important as you progress through your studies and learn in the future like more advanced techniques, it is very important to be very knowledgeable, to have like a deep understanding of these classical techniques, okay? Again, these are the things that allow you to just get a sense of what a good design will be just with a piece of paper and a pencil, okay? So what we will do is we will look at, stability, whether the system explodes or, is unsafe or, just very bad stuff, or actually kind of like it works and it's safe, and look at performance. Aside from being safe, is it comfortable? Does it have like a fast response, and things like that. Okay? And then look at how to design a system that satisfies my properties. Okay? Now, something we will do in this course is the following. As you may have noticed, I am not requiring you to buy any textbook. Okay? Instead of relying on a textbook, you will rely on this thing. So this is a little device that Julian and Mac, some of the teaching staff have designed for this course. The idea is that we are trying to keep the cost down so that every single one of you can get one, okay? So you're saving some money on the textbook. You may want to invest some money in this thing. So we are trying to keep the cost down. This should cost you less than $60, sorry, 60 francs. So essentially we are placing an order. We will get a bunch of these within a couple of weeks, and you will be able to buy one. It's not mandatory. If you really don't want it, you don't have to buy it. I really recommend that you do buy it, okay? Because this is something that will give you the opportunity to understand physically what happens when you make different decisions in terms of control, okay? And instead of staring at plots on the textbook and staring at the questions, what you can do is play with this thing, and you will see what is happening. And you can touch it, you can hear it, okay? So, so what is this? Essentially what you can, okay, the duck is optional, okay? So the duck is optional. I just put on this. So it's a little device, as we can call it like a seesaw, a little bit of a pun, because this course is about what are called seesaw systems. Okay, so this is the seesaw. Okay, I will explain what we mean by that. So this is a little, like a toy thing where you have this, this device can just rotate, this direction, has two propellers, right? And you can command the voltage in this propeller and the voltage in this propeller, right? And what we will try to do is try to maybe stabilize this seesaw at some angle, right? So you want to stabilize it at, say, 0 degrees horizontal. Maybe you want to stabilize it at an angle, right? Or maybe you want it to have like a sinusoidal motion or whatever other motion that you like, okay? And then we can play with it, just by itself, or we can put a duck on top of it, right? And then see what happens. How do you stabilize this thing when you have a duck or whatever your favorite toy is, sitting on top of it, okay? And I think that, this would be really something that you can just keep on your desk as you go through the exercises and, and you study the material, really get a good sense of what this is all about, okay? So we are ordering, so it would be useful for us to know how many of you are actually interested in buying one. We'll probably order a couple of hundred, and I hope that, that you will be interested in getting one. Probably we will collect, like orders in a sense. Maybe we can figure out the logistics for that, okay? Good, and by the way, this is something that you can just hook up to your computer, and then essentially what we will do in the exercise sessions is really understand how you can actually write a little program that makes your seesaw, work in the way that you want, okay? Good. This is how you start, right? Then in a few years you will be driving cars or flying airplanes, but let's start with that, okay? Okay, so the movies are not... let's see. See if this works. Okay, so this is, like a short video that shows how this, that should show how this thing works. The network is not cooperating today. Okay. Okay, so we turn it on, and we spin those propellers, right? And then we can. This was something that Julian put together quickly, so you had this thing, and you perturb it, right? So you kick it with the pen, and then your control system is such that will bring the seesaw back to horizontal. In this case, you will see that this is far from ideal in the sense that you have some friction in the hinges, you have that cable that is hanging from below. So what you will see is that you will write some equations, but the behavior of the system is not exactly like what you model in the equation. But this is the beauty of control systems in the sense that the feedback control, the techniques that we will develop allow you to be a little bit loose on the equations, on the modeling, because you can take care of all those disturbances by automatic control, okay? So I think that we actually didn't put a lot of effort in making this as ideal as possible, because actually I want it to be as not ideal, as realistic as possible, okay? In the sense that you will have a bunch of these non-ideal phenomena or non-ideal features that you will deal with controls, okay? Questions? There is some noise, some buzz. The excitement, you can hardly contain yourself for the excitement of this. Okay. Okay. So far so good, and this is the fun part that you can probably easily relate to, okay? So we have a system, and we want to control, how much I want to spin up this propeller, that propeller, to turn this seesaw this way, that way, so on and so forth, right? Now, an unfortunate reality is the following, that a lot of the cores and a lot of the techniques that we will develop are actually based on something that is called the Laplace domain, or the frequency domain, okay? So we will work with instead of working with functions that evolve over time, we will look at functions in what is called the S domain, the complex domain, okay? So what will happen is that in order to develop these tools, we'll have to go from the physical world to something that is a lot more abstract, okay? And there is a danger. I mean, it's not a danger. You will lose the physical intuition of what is going on, okay? As I wrote there, this requires a certain, leap of faith, okay? And actually, the learning curve can be quite steep, okay, for many students. I was one of those, okay? It took me a while to figure out all those things, okay? We will make every effort we can to emphasize the connection between this complex Laplace domain and the physical world. But, sometimes you may not get the intuitive feeling for that connection, okay? If that happens, look at the ducking, at your little widget. So you will see what the effects on the physical device are. So you will maintain that connection to the physical world, okay? On the other hand, my recommendation is just, keep calm, don't panic, just follow the rules, okay? So the reality of it is that a lot of this work will be done on this complex domain of things that have absolutely no intuitive physical counterpart. That's the bad part. The good part is that there are a number of rules and techniques and steps that you follow. There are a number of procedures. You can actually get pretty far by just following the procedure, just following the rules, okay? So there will be times in which you're following a certain number of steps and you have absolutely no idea what those steps mean. Follow the steps for now, okay? And that, some of that intuition will actually develop over time, will develop as you see the connection between what happens in this complex domain and what happens in reality, okay? So don't panic if you don't see the connection with the physical world, okay? Took me years to figure that out. Okay, you will not be alone, okay? But if all else fails, just follow the rules and you'll be okay. That includes doing well on the exams, okay? So don't panic, okay? Okay, let's talk a little bit about the logistics. Okay, so I'm the instructor of the course. My office in the ML building, just across the street, okay? The lead TA is Julian Zilli. Here he is, and we have a whole, he's a PhD student with me. Very good at what he does, very good knowledge of the subject. He took the class, a few years ago, and then he's been assisted by a number of other TAs, graduate and undergraduate that will help you through the exercises and so on and so forth. The assistant for the course is my assistant, Nina Fator. She sits in an office next to mine. Lectures, probably all of you know that, right, because you're here. Are on Fridays, 10 to 12, in this room, and there is another breakout room where there is a video feed. The exercises will be, on Fridays from 1 to 3. This will be broken down into several sections. I understand that Julian has posted the breakout of the sections and the rooms on the website, so you may want to check that out, okay? And also maybe discuss, like a section assignment in terms of, preferences for languages or scheduling conflicts or, whatever. But, please refer to Julian. I will have some office hours. I'll need to schedule them, okay? So we'll try to figure out something that works for everybody, okay? I will post lectures and the exercise notes on the website. I will try to do that at least the night before, so that those of you who want to do that can download the can download the lecture slides, the lecture notes, and print them out or whatever works for you. Okay. I uploaded these notes last night, but then when I tried to download them, they were last year's notes. Did anybody try to get the notes from the website today? Or the 2017? Okay, yeah. For some weird reason, last night I kept getting even though I had just uploaded the new notes, I kept getting the old ones. No idea why. Okay, so you can rely on the lecture notes. Of course, on the exercise notes, and of course, you can rely on the teaching staff, myself, Julian, and the other TAs for help, for reference. I'm also recommending a couple of books. These are not required, and I will not follow exactly the material on the textbooks, okay? So I'm not requesting that you use the textbooks. This is something that you can use if you want to have some additional material, some additional perspective, maybe some different perspective, right? So have somebody explain in a different way may be helpful, okay? But also, I don't want it to be confusing for you, okay? So just use these textbooks with some judgment, okay? Use them to the extent that they're helping you, not to the extent in which they're making things more complicated for you. Okay, the first textbook is a very nice one, and something else that I like. You can buy it if you want, or you can go online this is a textbook written by Professor Richard Murray. He's a professor at Caltech, and Carl Astrom, who is one of the fathers, of the field. He now teaches at Santa Barbara. Anyway, so if you go to Richard Murray's website at Caltech, you can actually download the PDF of the book. Okay, you can download it for free. You can buy the physical copy, for a charge, do as you like. Now, if you go to Richard Murray's website, you will actually see that there is a second edition of the book that is in the works. However, the second edition is still undergoing a number of changes, so for the time being, we will just use the first edition, okay? Feel free to use the second edition if you want some, new, updated. But, the material that we will talk about is really material that was developed, 40, 50 years ago, so don't expect to have a lot more new developments, okay, between the first and second edition. There is another book that you can use, and this is actually a book that, the book that was written by Professor Lino Guzzella, who was my predecessor, in the control systems, lecture, and then he's the president of the ETH. It's a great book, a lot of information, can be a little bit daunting in the sense that maybe a little bit too much information, okay? So again, use it with judgment, okay? So maybe you want to do like a first pass with just the lecture notes and maybe the Murray book, Astro Murray book, and then when you have a little bit more understanding, you can also dive in Guzzella's book, okay? Excellent book, but I think it has a lot of information, okay? A lot of information, maybe a little bit too early, okay? Now, something else that we do, and this was very successful last year, we will use this, it's a website, it's a web platform called Piazza, and this is a platform for online collaboration and forums and asking questions, and so you can ask questions as yourself if you want, or you can ask questions anonymously, okay? And other students in the class can also answer your questions, or the teaching staff can answer your questions, okay? Or we can collaboratively, build better questions. What I've seen is that the average response time between when you posted the question and when you got an answer was in the order of, like 10 minutes or something like that, okay? So, definitely, under 1 hour, okay? So this actually has been a very nice platform, and students last year used it a lot. We kind of we saw like a peak in the usage, around the exam time, but anyway. But yeah, so it's a nice platform that you can use to give feedback about the course, if there are, about really anything, and you can post questions anonymously. So, and I have absolutely no way of tracking who you are. And even if you post it not anonymously, I will not, track you down or something like that. So, good. Also, when students post answers, the teaching staff can actually mark those answers as, well, this is not quite right, or it's an excellent answer, and and edit those answers and things like that. Okay, so it's a nice tool. So sign up, and we will use it throughout the semester. Okay. It's a tentative schedule. So today we just an introductory class just to get to know each other. We will start talking about signals and systems. This will be mostly definitions. So in a sense, this is not stuff that you really need to understand in the sense that these are definitions. So just take them as granted, and then we will see how they're helping us throughout the rest of the course. Okay. So first lecture today, just looking at introduction, some definitions of what are signals, what are systems, what are some properties of systems that we like. The second lecture will be about how you actually model a system, how you write down equations that represent how a system behaves, okay? And this is really the part about modeling, okay? So, yeah, so this is modeling, okay? Then this is the second part, which actually you see that takes the, the most part of the course is about analysis, okay? So this is about, given a model of the system, given a bunch of equations that describe how my system behaves, what I will look at is how the system, will behave in response to certain inputs. We'll look at whether the system is stable or not. We will look at what are different factors that influence the behavior of the system, okay? So this is the analysis part. Okay, and in particular, we will start looking also at what happens when you take a system, you put it in a feedback loop. We will look at what feedback means. So essentially, you put in a feedback loop with a control system, and then what you want to understand is what happens after you close the loop with some control system. Okay, this is really what classical control is all about. Okay, and this is the part where we look at the analysis with the feedback, okay? Okay. Then once we have all the tools to analyze, to understand what happens if we do a certain number of things, then we will get to the last part of the course, which is the synthesis, okay? And this is the part of the course where we really learn how to design controllers that make sure that the system behaves in the way that we want, okay? The TAs are, actually quite good at front-loading some of this material in the sense that what you will see is that you will start getting a sense of what happens with different choices of control systems early on, okay? We don't have to wait until the end to see how to design a control system, okay? Good. So what we will do today. Okay, well, today, as I said, just introduction. So what we will do is try to look at what are control systems, what do we call control systems, and understand them in terms of functions that map an input signal to an output signal. And of course, we also want to understand what do we mean by signals, okay? What we want to do is also try to think about, okay, so what are different examples of control systems? What will be the inputs? What will be the outputs of those examples? We will want to try to think about, what will be the benefits of using control, okay? And then we have a number of properties and, like a classification of control systems. We'll go through them, okay? These are systems that are static or with memory or without memory, systems that are causal, systems that are non-causal, so on and so forth, okay? We'll go through, systems that are linear, that are not linear, so on and so forth. We look at different architectures for control systems, and so we'll learn to figure out how to distinguish between them, and then really concentrate on what is the objective of the class, that is single input, single output systems versus multiple input, multiple output systems, okay? Where do we have a break? At 5:02? At 11, okay, at the hour, okay. Okay, so let's keep going on that. Okay, so what are signals? I like to be a little bit formal and, to have, the math done right, okay? So a signal is really a mapping from a certain set that we will call T, okay, to another set we call W. T is really the time axis. For this class, you can think of signal as a function of time, okay? So in this case, we can just take as the set T is just the set of all times, just the real axis, okay? The signal space is, for most of what we do in this class is, again, would be the real axis again. So for example, this would be the position of the car, the lateral position of your car, or maybe the speed of your car, okay? Okay, and this would be the output signal in this case would be what is the speed of your car as a function of time, okay? these signals can take one value, or maybe these are vector signals, like a vector value signal. So signals that actually take multiple values. For example, in your car, when you look at the dashboard, you have something that is showing the speed of the car, something that is showing the RPMs, the revolution per minute in the engine, right? Or you may have, something that is showing the temperature of the oil, or something that is showing how much fuel you have in your car, okay, in the tank. So these are all different signals, right? You can think of just concentrating on one, or you can think of just looking at all of these signals as a function of time, okay? So these signals, in general, can be a vector valued function. Also, as I'm showing here, we can think of signals as time as something that just evolves continuously, okay? So now you have this function of time will be some kind of like continuous function. Or if you're, for example, if you're using some kind of a computer, then you can think of time as something that actually happens at, every second, okay? Or 10 times a second, right? So 10 times a second, you measure the output of some sensor and generate this function, okay? In this class, we will focus only on these ones. But in general, you can have different representations of signals, okay? So what is a system for us? A system for us is something that is really a map between signals that is, in plainer words, is something that takes some input signal and maps it to an output signal. For example, takes the angle by which I depress the gas pedal over time and gives me how the speed of the car changes over time. Okay? Is it clear? So the input signal in that case would be how the gas pedal changes. The output signal will be how the speed changes in the car. Okay? Both of these are function of time, right? Are they independent? No. Which one depends on the other, in a sense? So what's the difference between the input and the output? Can you set the speed, and then you figure out, and then the gas pedal moves? No, right? So typically what happens is the other way around, right? So you design, so you choose the angle, you choose how you want to move the gas pedal, right? And as a result, you will see some speed in the car. Okay? So this is the difference when we talk about an input signal. The input signal is a signal that typically you can manipulate. Okay? So this is up to you to change. Okay? Then the output signal is something that, depending on your input and depending on your car, right? So if you have a smart car, or maybe you have a Ferrari, of course the response to the angle in that gas pedal will be different, right? So depending on your system, you will generate different outputs, okay? And essentially this is the effect of that system, okay? We will see that not all input signals are necessarily up to you to control. Sometimes we will consider as input signals something else that is beyond your control, okay? For example, could be you're flying your airplane and then you have some crosswinds or some headwinds, okay? So clearly the fact that you have a headwind will affect how the airplane flies, and clearly even more so a crosswind, right? So now you get a wind gust, and now your airplane will start doing something weird, right? That's not something that you are controlling, but this is still something that affects how the airplane behaves, okay? So, so typically these are called the, technical term is exogenous inputs. So exogenous means generated externally, right? So these are inputs that are not set by you, but are set by nature, or set by the world, okay? Okay, let's take a break and then we will resume from there. Okay. Okay, let's get started again. Okay, so we're talking about inputs and outputs. So some of the inputs typically are inputs that you can manipulate, inputs that you can choose, that you can design. You can choose, what signal to send. These are also called endogenous inputs. Endogenous means generated internally. Okay. Exogenous inputs are things that are generated externally by somebody else. It can be nature, an opponent, some bad guy interfering with your system, right? And these are typically these disturbances, like a wind gusts, or maybe the weight of your car, how much fuel you have on it, how many people you have riding in the car, what is the surface of the pavement, right? So are you driving on tarmac, on like a pavement, or you're driving on gravel or on dirt, right? So these are all things that can affect your behavior, but they're not entirely under your control, okay? Also, some other sources of exogenous signals are things like noise. So, for example, when you're trying to measure the speed of the car, you rarely have the exact value of the speed of the car, right? So these are all instruments that are affected by some noise. And what you will have is that maybe your measured speed will actually fluctuate, hopefully around the true value, right? But will fluctuate, right? And that fluctuation is the noise. And this is another input that affects your system behavior, okay? So the way that we write these things is the following. Again, I like to be a little bit precise with the math and things like that. Don't get scared. There's nothing, too fancy about that. But okay, so what we will use is, as a system, so we said that the system is a map from an input signal to an output signal, okay? In this class, this is what the system is, okay? So essentially what we have is a certain signal. Okay, so this will be, so we have T, and then this is U, okay? So then when I write U, okay, what I mean is the whole function, okay? Is the whole signal, okay? If I pick one particular value, okay, so that would be U at time T, okay? You see the difference. U is just the name that I give to the whole curve, the whole function. When I write U parenthesis T is the value that that function takes at a particular time, T, okay? Anyway, so what we have is this input signal. Think of it, this is the profile, the angle of the gas pedal, right? And then there is something that happens. Okay, this will be for example, my car. Okay, this will be the speed. Okay, this is my car, and then what happens is that now what I have is is not speed. This is the gas. Okay. And here what I have is the speed, right? And the speed will be something like that, okay? And again, I will call the output signal, we can call it Y, right? And Y refers to the whole function that gives me the speed as a function of time. And then if I pick one time, then I have, one particular point on this curve will be the value of Y at time T, okay? So, then my input-output model is something that takes my input signal and transforms it into the output signal, okay? I will call this sigma, okay? So this is my system. Sigma stands for, the Greek S, okay? Stands for system. And, this is something that transforms U, that is my input signal, into sigma u, that will be my output signal y, okay? What this means is that, the way that I write these things here is, in this case, I'm just writing as this input-output model as something that takes one signal u and transform it into another signal y, okay? You can also write this thing in terms of what happens at every single point in time, and then what I will write is, y of t is equal to sigma u. Okay, notice how I put parentheses here, okay? So I really don't want to write y of t is equal to sigma u of t, okay? Why not? Because u of t is just a number, okay? And then sigma is something that operates on signals, that is, operates on functions, okay? So then what I want to do is really do something like that, where now sigma u is another signal, okay, that is obtained from the signal u applying this operator sigma. And then what I have is sigma u, which is another signal, evaluated at time t. And of course, this needs to be valid at all times, okay? Very often we will use this block diagram representation where we have a certain input that travels on this line. Then we have my system sigma, right? And then the output of this block, what I have is another sigma y, okay? This is a very convenient way of writing down. This shows exactly what are the inputs to this block, right? So you have this arrow that is going into the block, and then you have this other arrow that is coming out of that block, okay? So clearly u is the input, y is the output. Questions? Okay, so what are the inputs and outputs for the little seesaw? Anybody? Yeah.
Input are the signals that can be manipulated.
I think that actually is better if you use this thing.
Test. Well, the inputs are the signals that can be manipulated by the designer.
Right.
Something
in this
like
particular
this.
case, what do you think that we will manipulate?
Well, reference to the car, I guess. If the street makes a curve, we have to evaluate how to take the sum. I don't know the signal, the map signal, how to make the wheel turn around.
Think of this particular little thing, this particular toy widget. Test bed. Okay, let's call it test bed.
You mean like in this one? Or?
Yeah, in this one. Okay, so now we have this thing.
Yeah, maybe the position of the propeller of this
we actually
cable.
have no way of controlling that exactly, directly, right?
The power source.
So essentially, we will connect this thing to a power source, right?
Yeah.
But then, what is it that we can decide? What is it that we can change?
We can change the amount of power each wheel or propeller can have.
Right?
Yeah.
So, yeah, thank you. So the input to this system is actually, what color should I use? Okay, so the input to the system will actually be the thrust that I generate on this propeller, right? And the thrust that I generate on this propeller, right? Okay, so how do I control the thrust? Essentially, the more voltage I send to that particular propeller, to that particular motor, the faster that propeller will spin, and the more lift and thrust I will generate on that particular propeller, okay? Now, since we have two propellers, two motors, right, and these can be actuated independently, right? Now, how many inputs do you think that we have? Want to hand it down or hand it back, or somebody else wants to have it?
Should I talk or is someone?
You're stuck with it forever.
Well, I'm just guessing maybe just two.
Two.
For each propeller.
Yeah, right. So we have independent control for each one of the propellers. Okay. Now this is something that now can throw you off, because now what we will see is that now we have the input signal is actually a vector signal with two independent components. On the other hand, what do you think will happen if I send the same command to both propellers? The little seesaw will desperately try to take off, right, and fly. But hopefully it has been designed in such a way that we'll not be able to. Okay. So if you send the same command and both the propellers are generating the same thrust, then actually nothing happens, right? Because, yeah, it's trying to lift the little thing up, but the propellers are not powerful enough. On the other hand, if I generate a different thrust on each propeller, what do you think will happen? Now, on this side, this is pushing more than the propeller on this side. So what happens? No math involved, just simple physics, intuition. What do you think will happen? You can pass that around. Anybody?
The angle starts to change.
Right, exactly. So whenever there is a difference in the thrust generated by those propellers, then you're generating a torque, right? And then the consequence of the torque is no longer that the whole thing tries to lift off, but now the seesaw will start to rotate. Okay? So that's actually what we will control. Our input signal will actually be, okay, so this is an input, right? Okay, so let me write it here. So the input, and what we will send, to here essentially, and this will be moved to the motors, is actually the command of T2 minus T1. Okay, this will be our input. Essentially, is the difference between the two. I can send T1 and T2, but really what we care about is the difference between the two. Okay? Because this is actually what will cause the seesaw to turn one way or the other. Okay? So technically we have two inputs, but practically we have one. Okay? Because really the only thing that matters is the difference between those two thrusts, because the sum is just trying to lift off the whole thing. Okay? What are the outputs? The outputs, okay, so what we will have on this little device are an accelerometer. Essentially, the accelerometer is, and the accelerometer is mounted in the middle, right? Yeah. So the accelerometer is mounted here, okay? And this is something that is measuring is really measuring gravity. Okay, where gravity is with respect to to this device. Okay, and this is something that you can use to measure what is the angle at which this device is sitting. Okay, and also what we have is these other things. These are the gyros, right? The same place. Okay. So not only that, we also have some solid state gyros. These are actually devices that measure the angular velocity. Okay? So essentially what we are measuring is the angle, okay, the angle at which that seesaw is at, and also the speed, the angular velocity at which this seesaw is rotating, one way or the other. Okay? So you see that now in this case, again, what we have is, what we are measuring is the angle of the seesaw and its derivative. Okay? This will be the outputs that you will be able to use. Again, technically, these are two outputs. Okay? In practice, depending on what you're doing, you may just use one of them. Okay? And in general, this can be seen as something that measures the angle plus its derivative. Okay? So it's one signal again. Okay? Can you give me other examples? So in a thermostat, what are the inputs and what are the outputs? So now what you have is a device, like a heating device or air conditioning device. What is the input in your heater? Anybody? Yeah? Okay, perfect. So this is, okay, so the voltage or current or whatever you send to the, to this heater, right? What is the output? Yeah, typically you don't really care about, so that's the output of the heater in a sense, right? But really when you think of it as a device that you use to heat up a room, what is really that you measure? What is it that you really care about? It's not the heat transfer to the room, right? So you don't really care about that. I mean, that will affect the bill that you get at the end, right? But what is that you care about when you're heating the room? Yeah. The temperature, yeah. Okay? So what the input, the signal that you can manipulate is whether you turn it on or off, for example, right? That's actually typically what you do with heaters, right? You don't kind of like regulate it continuously. You just turn it on or off, right? So then the input signal is heater on, heater off. The output signal is what is the temperature in the room, okay? Other examples. I don't know. Okay, so when you're sitting in a car, what could be like input? It's an easy one. We've been talking about cars since the beginning. What is your input when you're steering a car? Okay. Steering wheel? The angle of the steering wheel, yeah. What is the output? The direction of the car? Yeah, it could be the heading of the car, or maybe the heading rate, right? How fast the car is turning. Yeah. Anybody has other more complicated things in mind? These are the usual ones, right? So, okay. Is it clear? I mean, of course, you have a whole lot of different examples, right? But typically what you have is something that you control, right? In the sense that you can decide to switch the heater on or off. You can decide to push the gas pedal. You can decide to turn the wheel, right? And then what you're trying to affect is the temperature in the room, the speed of the car, the angular rate of the car, and things like that, okay? These are the inputs and outputs. Okay? Now, given a system, we can have a bunch of different properties, okay, that we'll talk about and affect some, the way that you can do control design and things like that for the system. Okay, so a first categorization is whether the system has memory or not. Okay, a system is said to be memoryless or be a static system. Is essentially, I can compute the value of the output at some time t just as a function of the input at time t. Okay? Let me give you an example. So this system here, so y of t is equal to 3 times u of t. What do you think will happen? Okay. Okay. So this is time. And let's say that I decide my u to be it's 0, and then at time 0 becomes 1. Okay? This is my U. How do we compute the output? What would be the output, for example, at this point? Yeah. Zero. Awesome. Okay. So the output here at this point, you just take the value of the input at that particular time, multiplied by 3, you get the output at that time. Okay. So what will be the output at this point? What we said is that this is actually 1. Okay. What will be the output at this point?
Well, 3 times 1, so 3.
Man, you're good. Yeah. Okay. So in order to compute the value of the output at this point, you just look at what is the value of the input at that point in time. Is 1. So the output will be 3. Okay. So what you will see is that the output signal will be something like that. Okay. So at any time that in order to figure out what is the value of the output at some point in time, you only need to know what is the value of the input at that point in time. This is a memoryless or static system. You see why it's memoryless, right? So the value at this point does not depend in any way from what happened in the past. Or, by the way, does not depend in any way from what will happen in the future. Just depends on what was the particular value of the input at that particular time. Okay? So this is a very simple system, something that just takes, a signal and operates some function, applies some function, time by time, okay? Without knowing other parts of the signal at all, okay? This can be something like simple as just multiplying by 3, or can be something that is arbitrarily complicated, right? So now I just say that y of t is just some function that I had to take u of t, compute the square, take the sign, and then take the square root, whatever, right? But you see what I'm doing is I'm doing a sequence of operations on u of t that is just on a number. I'm not doing operations on a signal, okay? Let me give you an example of something that is not a static system, right? So, for example, I can decide that my input is actually the integral, that my output is the integral from -infinity to time t of my input. So what would that look like? Let's use the same colors as before. So now what I have is, I have time, I have my input signal that is 0 for negative time, and then becomes 1, okay? At time is equal to 0. What do you think the output will look like? Yeah?
It might be a linear equation going diagonally upwards.
Almost, yeah. But let's get there, carefully, okay? So, for example, what do you think is the value of the output at this point?
That would be 0.
0, right? And up to this point, the value will be 0, okay? Okay, so the output would be something like this. It would be 0 up to here, and then what happens? Fantastic, awesome, right? So then, at this point, at this point, okay, so just to the right of 0, what would be that area? Is the area of a little slice of that, of a little rectangle, right? So there would be something that would be positive and small, right? And then, as you can understand, I hope you understand that as time goes by, this is something that is actually linearly increasing, right? As she correctly said, the area of this rectangle, right, keeps increasing linearly as I move my time t to the right. Okay? So you see that now, you see that this is not a static system, right? Because in order to compute the value of the output at this point, it is not enough to know only what is the value of the input at this point, right? So this is a system with memory, right? Because now the output at this point depends not only on the input at this point, but on the whole history of what happened to the input in previous times. Got the difference? Okay? Good. Fair to say that, or needed to say that, all interesting systems actually have some memory, okay? Okay, and that's something for which we cannot just take the input and multiply by some number or apply some function and we get the output. What we need to do is feed what was the whole history of the input in such a way that we can determine what the output is at some time. Okay? Good. Time invariance. Okay, so time invariance is really something that depends on the following. So, I say that the system is time invariant if, so you see the definition there, okay? We'll go through the definition in a second, but what does it mean in plain English, okay? How do you explain to your grandma what a time invariant system is? A time invariant system is one that does not depend on the value of, for example, of the wall clock time, okay? Essentially, is a system whose behavior does not depend on what time it is. Okay? Can you give me some examples of systems that you think are time invariant versus systems that are time varying? Think of the, say, heat control in your house during the summer. Your house is being heated up by your heater, right? But also by the sun, okay? So you see that you can understand that the behavior of the temperature inside the house when you turn on the heater or on or off depends not only on the heater, but also depends on where the sun is, depends on the time of day, okay? Whereas typically when you have a car, does the way that your car behaves depends on the time of day? Not really, okay? Okay, so essentially a system is time invariant if the way it behaves, the way it works, does not depend on what time of the day it is, okay? How do we write it mathematically? Kind of like a neat construction. So essentially what you do is the following. Let's define, this is another system, right? So, and this is the time shift operator, let's call it sigma tau. Essentially, this is a time shift of tau, okay? So essentially what we do is the following. We take some signal, okay? And then what we do it is pass it through this system sigma tau. And what we will get is something that is the same signal, but is translated by some tau, okay? So let's say this is at time t, and this is at times t minus tau. Okay? So essentially what you find, sorry, this is, let me correct this. Okay? So essentially what you have on the right-hand side is exactly the same signal, or let me do it in a slightly different way. So we have a signal that just is 0 for all negative times, and then becomes 1 at time 0. Okay. Then we move it through this time operator, sigma tau. And what we get is a system that is 0 up to time tau, and then becomes 1. Okay? Right, so if this is tau, okay, you see that the value of the output signal at time tau is equal to the value of the input signal at time tau manu tau, that is 0. That is, essentially, this is the value here is not really defined, but is the point where the signal goes from 0 to 1. Okay? So this is the mathematics. But what happens in reality is that you're taking this signal and you're just shifting by a time tau. You're just delaying by some time tau. Okay? So this is the time shift. Okay? And the system is time invariant if it commutes with the time shift operator. That means that I can just apply the system to the shifted input signal, and what I get is just the shifted output signal. Okay? See what I'm saying here? This may sound a little bit complicated. Essentially, what happens here is the following. If I give this as an input, okay, and maybe I get that as an output, like what we saw before, okay, then if I time shift the input, okay, so this is just the same input that I gave before, it's just time shifted. What do you think should happen if my system is time invariant? If I shift the input, that is, I reset my clock, right, my watch, and just change its time, or I move time zone, or just wait 1 hour to run my experiment, what will happen is that the output will be shifted in exactly the same way. Okay? If this is Y, and this is U, this is sigma tau Y, this is sigma tau U. Okay? And essentially what we are saying here is that sigma tau Y is what you get as the output when you feed to the system sigma, the signal sigma tau U. Okay? Notice that when I write, I know that Y is equal to sigma U, right? So this will be sigma tau, sigma U. And now if you compare this one to this one, you see that U is equal to U, right? So essentially what we are saying is that sigma tau, capital sigma, is the same as capital sigma, sigma tau. Right? Because what I have here on the left is exactly the same as what I have here on the right. Okay? This in mathematical terms means that small sigma commutes with capital sigma. I can just swap them. Okay? This is the mathematical definition. Definition to your grandma is the behavior of the system does not change with the time of day. Okay? Linearity. So this is actually the key property that we will use. So what I will say is that an input-output system is linear if for all input signals, UA and UB, and all scalars alpha and beta, if I apply as an input a linear combination of my two inputs, what I will get as the output is a linear combination of the outputs, okay? So really the key property is the property of superposition, meaning that if I know that if I apply the input UA, I will get the output YA, and if I know that if I apply input UB, I will get output YB, then I know that if I apply UA plus UB, the output will be given by YA plus YB, okay? So this is what we mean by linearity. And this is the key property that we will be using throughout the course. And really the key advantage of linear systems is exactly that of allowing superposition. So in everything we will do, we will essentially divide and conquer. Whenever we are looking at some complicated input function, we will try to decompose it into smaller pieces. We will compute what is the output of that smaller pieces, and then we will combine everything again to construct what is the output to the more complicated input function, okay? Causality. This is another thing where I like to get with the math, but again, I give you first the explanation to grandma. A system is causal if its behavior up to time t only depends on what happened before time t. Okay, maybe including time t. Okay, so essentially, a system is causal is the input only depends on the past and possibly the present. A system is strictly causal if it only depends on the past. Okay? So how do you define it mathematically if you really want to be precise? So what you will do is you can define a truncation operator, P, such that is essentially defined this way. Let's say that I have some input function, input signal U, okay? Then if I truncate it at, say, capital T, then my truncated signal is the same signal up to time t, and then goes to 0. Okay? What does it mean? So then, then we can define causality in this way. I say that the system is causal if this expression holds. Essentially, what you can do is look at, essentially what I will do is look at the difference between what happens if I apply my whole input signal versus what happens if I apply the truncated input signal up to time t. Okay? Now, what I say is that my system is causal if the behavior up to time t is the same in both cases. Clearly, what happens after time t will be different, right? Because in one case, I apply the whole signal, in the other case, I truncate it. But the key point is to look at what happens after time t, okay? And if this is true, then what it means is that my behavior up to time t does not depend on what will happen to the input signal after time t. Now, do you imagine, can you give me an example of a physical system that is not causal? Well, I wish I had one because I would win the lottery, every time, right? So all of your physical systems will have to be causal. So, and the way, the reason why we talk about causality is that you will have to remember that, if you do the math, it's very easy to construct systems that are actually non-causal when you do the math on the paper. But then the problem is that you will never be able to actually implement them, okay? So anything physical will have to be a causal system. Just remember that, okay? Because something that is non-causal means that you're reading into the future, right? So now you have a system that depends on stuff that is going to happen in the future, okay? So all physical systems will have to be causal, remember that, okay? And what this means is that if you want your control design to be physically implemented, your controller will need to be causal, okay? Keep that in mind. So in this course, we'll only consider systems that are single input, single output. That is, the input signal is just a scalar function of time. The output signal is a scalar function of time. They're linear, they're time invariant, and they're causal. Okay? It so happens that most systems are actually not linear time invariant. In particular, they're not linear. Okay? But the power of this class, or the power of the techniques developed in this class, is that even though most systems are not linear, pretty much all of them can be approximated by a linear system. Okay? So then you take the real system, complicated, the little seesaw, which has all the cables hanging and friction and stuff. You can just model it as a linear system. Just forget about all the complicated nonlinear stuff. You can design a controller for the linear system, and lo and behold, your controller will actually work on the real system as well. Okay? So this is another key point in this class. So even though we know perfectly well that real systems are not necessarily linear, what we know is that what we can trust on is the fact that all of them can be modeled very well by linear systems. We can design a controller based on the linear system and apply it on the real nonlinear system. Okay? Good. I think that we don't have time to cover this, but anyway, we can get started. So we looked at this block diagram, right? So we have a system, we put in this block, we have an input coming in, and then output coming out, okay? Now, the nice thing with this system is that we can interconnect them. For example, we can have two systems, and I can have one system, which has some input U, some output. Then this output can be the input to a second system, okay? And now I have this output that comes out of the second system. If I interconnect systems this way, this is a serial interconnection. You can see that my overall system can be just written as sigma 2, sigma 1, okay? Because I can, this would be, this is sigma 1 U. This will be sigma 2, sigma 1 U, okay? So then you see that the overall effect of the serial interconnection is just sigma 2, sigma 1. Or I can interconnect these two systems in parallel, okay? So now what I have is my input signal that goes into sigma 1 and also into sigma 2. Then I have some output here, some output here. I add them up. And what I get is this will be sigma 1 U, this will be sigma 2 U, and the output will be sigma 1 U plus sigma 2 U. Okay? So then I can write that my sigma, my interconnection is written just as sigma 1 plus sigma 2. Or another thing that I can do is the following. And by the way, this is exactly what we do in feedback control, is I can take the output of the first system, use it as the input to a second system, okay? And then I can generate the input to the first system by subtracting this input U and the output of the second system, okay? You can do the math, and then what you will find is that, this is the way that you represent the overall interconnection. We will look at this equation, pretty much every week, during the course, okay? So don't panic if you cannot understand now. But essentially, the point of the feedback interconnection is the following. Next time, okay?